Okay, so hi everyone, Senan this side, and in this video we are going to see this validate binary search. Okay, so you would be given a root of a binary tree. Determine if it is a valid BST or not. So what is a valid BST? The left subtree of a node contains only nodes with keys less than the node's key. The right subtree of a node contains only nodes with keys greater than the node's key. Both the left and right subtrees must also be a binary search trees. Okay, that is fine. Now if this is the case, so all the nodes to the left is less than 2, that is true, and all the nodes to the right of 2 is greater than 2, so this is also true. In this case, if you see, all the elements towards the right of 5 is not exactly greater than 5, right? So this 4 is less than 5, this 3 is again less than 5. So this subtree in itself is a binary search tree, but because of this 5, we can say that this is not a valid binary search tree. Now how can we do this? Basically, one way could be to get the in-order traversal of a binary tree, this BST, and what will that be is that the in-order traversal of a BST is always a sorted array. So one way is you could find a valid in-order traversal, and then what you do is just check if the consecutive elements are in increasing order and none of them are the same elements. So if that is the case, you would have your search tree validated, but we are not going to do that. What we are going to do is observe the fact that in this right subtree, right, given this tree, what do I need to ensure on this right subtree that I know for sure that this could be a valid BST, right? So when I'm checking this side of the BST, I need to somehow have the information that all the elements in this tree is greater than 5, and when I'm searching for this node 1, I need to have the information that all the elements in this BST should be less than 5, and so that gives us a bound. So basically, this node, whatever this may be, right, if this tree is a valid BST, whatever this node may be, this should be greater than 5, this should be greater than 5, this should also be greater than 5. And how do we keep track of that? We would define limits of each node. So I know for this node, my limit is from 5 to infinity, right? Any number between that is a valid number in this node. Now let's say this value is, let's say 10. So 5, then 10. So I know this node should be greater than 5 and this node should be less than 10. And if the value is in between that range, that means this could be a possibly valid value for this node. So that is what we are going to do. We are going to define the limits. So what I do is, given this tree node of root, I give this root and I say the left limit is long min and the right limit is the long max. Why long min and long max? Because our values could be as big as int max and as less than int min, right? So I am taking numbers which are greater than this number. So let's look at this helper function. What we are actually doing is this takes the node, this takes the left limit, this takes the right limit, and does the comparison. So what I am saying is, if root is equal to null, that means a null tree is a valid BST, right? Because there is nothing, so I return true in that case. Otherwise, I check if the right limit is less than the root value, less than or equal to root value. That means it is beyond the range specified for this node. Or if the root val is less than the left limit, so the value should be in between this, right, left limit and right limit. In either case, the root's value is beyond this interval from left limit to right limit. What I do is return false. I am at a node that is not satisfying the constraints of a BST. Otherwise, what I do is I check for the left node and the right node if they are a valid binary search tree. Now for going to the left, right, so my left limit would stay the same, but since I'm going towards the left, every element on the left tree should be what? Should be less than this root's value, right? So every element on the left of this root node should be less than 2. That is what I'm trying to say. So the right limit is now updated to root's value and the left limit could stay the same. On the other hand, if you see on this recursive call, for the right side of the child, I should have all the values greater than the root node. So basically the left limit. So all the values to the right of this node 2 should be greater than 2. That is what I'm trying to update this to. And the only reason I'm doing this left limit and I'm taking this long is because I don't want to have to, right? So since I'm checking this as equal to and this also as equal to, what I could have is, let's say for a root node, a single root node with the value int max, right? So this condition would true this or either this one, right? int max, or if I get int max or int min as a root value, I would just return true, I would just return false. But let's say the tree has only a single node, so and that had a value of int max or int min, that would be a valid BST. I would have returned false. So to take care of that, I'm using long just to keep track that even if I get int max or int min, I won't return false if it is a valid BST. Also, it's since every node value is a valid, what do I say? It's a valid integer, so there won't be any case of having a long max or long min in this node value. So yep, that was the whole video about. Let's discuss the time and space complexity. So what is the time complexity? At the worst case, we would look at all the possible nodes, right? Because at any node, an issue can the node is not satisfying the constraints of left limit and right limit. So to check that, I have to see all the nodes at least once, and that is what I would be doing. I would check all the nodes, right? So that would be the time complexity. What would be the space It's not a constant because you are calling the function recursively, right? So at max, the height of this recursion stack space would be the height of this binary search tree, the maximum height, because you can not call any more recursive calls because you'd be at a leaf node, right? So the space complexity of this function would be the height of the maximum height of this binary tree, or basically the height of this binary tree, and the time complexity is the number of nodes we go off. So in general, roughly binary search trees would have a height of log n. So you can in a way say that the height of the space complexity would be logarithmic of n, and the time complexity would be big O, where n are the number of nodes. That there is also a case where you have a skewed tree, right? Like a linked list. So in that case, you have to travel the whole n nodes into the depth. In the worst case, this would go to big O of n, and for both time and space complex. But let's say if the binary search tree is also balanced, so in that case you would have a log n height. So that was the whole video. Hope you got something out of this, and stay tuned, and I'll see you in the next video.